In this video, I'm going to do some similar adjustments to the accelerator. I'm going to adjust the parameters that affect the electron beam energy. And in this case, I'm going to adjust the Klystron pulse voltage, which will affect the output RF power of the klystron. So this is different than adjusting the input RF power, because now we're adjusting the pulse which directly accelerates the electrons through the klystron. So what I'm going to do now is I'm going to, I've reset the accelerator back to the 15 MV beam, and I've reset the base parameters for the RF driver, the Klystron voltage, and the bending magnet. And I'm now going to explore what happens when we change the Klystron pulse voltage. I'm going to lower it first from 125 to 118 kilovolts. And then I'm going to sweep it back through over 125 kilovolts, and we'll see the change. So I'm going to drop this now from 125 kilovolts down to 118. And we're going to, when we do this, we're going to watch what's happening to our dose rate. It's going to go from 345 down to 0.96 centigrade per minute. So basically a very small dose rate, and that's because we have a very low target current, and that's because we have a very low RF power coming from the klystron, which is only producing 13.23 MeV electrons, whereas the bending magnet is letting 15 MeV electrons go through. So now if we go back and we increase this again, so if I'm going to go from 118, I'll go back up to 120. And we're going to watch our dose rate's going to come up again, 22 centigrade per minute. We have 13.7 MeV, which is increasing toward closer to 15. We have an increased beam current. I'm going to now go to say 120, 122. Now we've got quite a rapid increase in dose rate, 123 centigrade per minute. Our energy is now 14.16 MeV, which is getting close to the 15. So our dose rate has increased. I'm now going to increase again. Let's go to say 123. Now we're going up to 204 centigrade per minute. Our energy has increased quite a bit, 14.3 MeV, which is closer to our 15, and then which gives us a higher dose rate. Now let's go to 124. For the Klystron pulse voltage, now we're at 284, 14.55 MeV, and then which is getting closer to 15. Let's go to now 125, which is our starting point. So we get back to our original starting point. We have 14.73 MeV electron beam from the accelerator. If we go to 126, now we have 14.9 MeV. We have a dose rate of 375.9, which is getting quite high. If I go to 127, we've gone past 15 MeV, so now our dose rate is 375. And what we should expect now is that as we increase the Klystron pulse voltage, our energy, because now we have more RF power coming from the klystron into the accelerator, we can now make a higher energy beam. So we're going to have a decreasing dose rate again because our energy now is going to be too high. So if we do this again, so we go now to say 128, our energy goes to 15.21, which is higher than what the bending magnet is allowing to go through, and our dose rate is beginning to drop. It's now down to 350. If I go to 129, we now have a dose rate of 310, and that's because our energy is gotten too high. And I can just keep on going, so I'll go to 130, and we see a decreased dose rate, higher energy. I can go to 132. Energy is now much higher than 15. Our beam current is dropping again, and our dose rate is dropping off. So what I'm going to do now is I'm going to reset the Klystron voltage for 122 kV, and I'm now going to adjust the bending magnet like we did before to see if I can regain the high dose rate. So I'm going to go down from 131 down to 122 on the Klystron pulse voltage, and if we now have a energy of 14.16 MeV. Our dose rate is 123. And that's because we have a lower beam current on the target. So I'm going to decrease the the bending magnet current. I'll go down to 150. We have now a higher dose rate, 288. That's because we're allowing more electrons to get through to the target. because we've dropped the energy of the pass-through bending magnet. I'm going to now drop this again. So go to 145. So now we have a pass-through energy of 14. We have a dose rate of 293 centimeter per minute. But now we see that our energy of the electrons getting to the target is lower now than what the accelerator electron energy is, and so we see that if we keep on decreasing the bending magnet current, what should happen is we'll have a decrease in dose rate, because now we're looking for an even lower energy to go through the bending magnet. So when I hit enter now, our dose rate will drop off even further. And that's because our bending magnet now is only allowing electrons of 13.5 MeV through, which is lower than the accelerator set energy of 14.16, which is what happens because of the reduced klystron pulse voltage. So this is a similar scenario as last time when we just adjusted the RF driver to the klystron. So what we've done is, by adjusting the RF power, we change the electron beam energy coming from the accelerator, which changes the amount of the amount of electrons which strikes the target, because without changing the bending magnet to compensate for that, we will have a reduced target current, which affects our dose rate. So what we'll do in the next lecture is we will explore a similar effect, whereas in this case, we're going to leave the RF power constant, and we're going to change the amount of electrons going into the accelerator, and we're going to see what effect that has on the dose rate for the accelerator.